Hello there. In this video clip, we want to cover some fundamental stuff about space-time when we're looking at astronomy. And some topics that come up that are unavoidable the more you study the cosmos and astronomy are the concepts of space-time and the physical laws that govern space and time, such as relativity, special relativity, and general relativity. So in this video clip, we're just going to cover special relativity. I'll give you a little overview on special relativity versus general relativity, but we'll cover general relativity in a separate clip. So some of the things that come up when you're doing astronomy is you look at the night sky, you're looking at the cosmos, and you start to get an idea of the vastness, the size, and the scope of the cosmos, the distances that we're working with. When we're looking back at time and we're looking at the earliest galaxies, let's say the Hubble telescope photos show, going back 13 billion years ago and 13 billion light years across. So what does that mean? Well, we're looking back in time and we're looking at the history of those galaxies. And we're looking at how the light is traveling to reach us across that space. So one must start to consider, okay, well, how do we define the coordinates of space? And how do we define the coordinates of time to make those measurements? So we get into some very, very deep thoughts. And to begin with, let's think about, what do we mean by space-time? So when we study the very beginnings of the universe, we look at the Big Bang and the birth of it all about 13.8 billion years ago. So at that moment of the Big Bang is when time and space begun. So time was zero at the Big Bang, and ever since, space has been expanding and our time has been increasing since then. The arrow of time has been going forward, so to speak. So when we talk about relativity and look at the effects of relativity in cosmology or in astronomy in general, we look at the coordinates of space and time, and we use something called Minkowski space to define spatial and time coordinates. So that's something you don't need to know when you're just doing like an introductory course. For space, we're used to defining any single point in space by the coordinate x, y, and z. So if I want to take any point out in space, I would say, well, here is its position horizontally, here's its position vertically, and here's this third dimension position. Okay, I can take any point in a room and I can define it by a length, width, and height coordinate. That would be the x, y, z coordinate, the Euclidean coordinate, so to speak. Okay, and here we deal with a fourth dimension called time. So we use this with relativity. The fourth dimension is time. So any event in space is defined by this coordinate, and any position is defined by this coordinate. So if we wanted to track a comet through space, we'd give it its three spatial coordinates, and we'd give it a time coordinate. Okay, very important idea. So that's what we mean by four-dimensional space-time when we're talking about relativity and cosmology in general. Now there's a lot more fancy theories out there, but this is what we're going to restrict ourselves to. Okay? And some of the other questions are, well, if I'm conducting experiments on Earth and I'm trying to compare it to, let's say, some civilization we discovered around another star, would we have the same laws of physics that we could compare to? Would we measure the speed of light the same? Would we measure things like the force values the same? Would our lengths of a meter be the same, etc.? So do they hold everywhere in the universe? Yes, well, this is something that we'll see with relativity. Okay, are the measurements the same in frames of reference? And what is a frame of reference? Well, is there an absolute frame of reference? These are some of the questions that Albert Einstein and many others before him, so there's a big staircase of scientists that led up to special relativity that also asked the same questions and built upon the answers that we now have. So the other big question is the speed of light the same everywhere? Is it this constant value of 3 times 10 to the power 8 meters per second? And the conclusion is yes. Can anything travel faster than the speed of light? No. You might get some bizarre values, but that might have to do with reference frame transformations, how you communicate the laws of physics from one place that you make the measurements to another. Okay? And what other interesting effects do we discover, especially in astronomy, when we have objects that approach the speed of light, if any? What are some of these effects that we see? And what do we mean by time dilation, the twin paradox, length contraction, the pole in the barn paradox, relativistic energy and relativistic mass, the famous equals mc squared equation? How do we relate all this? And the big deal is relating it to our theories of relativity, in this case special relativity. So let's take a glimpse at special relativity. Okay, quick little overview on the differences between special relativity and general relativity. What are they? Which one came first? Well, special relativity got published in 1905, and that was published by Einstein, and it was based a lot on some work by other scientists like Lorentz and a few others. So there's a lot of stepping stones that built up to this publication in 1905. And general relativity came later in 1916. So special relativity dealt with how the laws of physics translate from one place to another. How we could translate from one frame of reference like on Earth to another frame of reference like the moon. So it was all about translating the laws of physics and also looking at the speed of light being constant and the consequences of having the speed of light constant. So we could say the constancy of the speed of light. That's just a very brief overview. Now, general relativity, on the other hand, was a complete theory of gravity. It took the work of Newton and was able to completely explain all the orbits of planets, etc., in having gravity be a condition of space-time. So this is a complete theory of gravity, which is a very mathematical description in general relativity, and whereas gravity is something, a condition of the space-time continuum, or for short we'll say a condition of space-time. So that took the approximations and gave an absolute theory where we could predict orbits and other gravitational phenomena completely. Okay, so there's a lot of experimental verification for both these theories. They've been tried and tested over decades and decades. So there's multiple experiments that show these to be accurate and true. So they've both been experimentally verified over and over again. So it's not to say that the old theories are not any good anymore. They are really good approximations. The time where we want to use the tools of special relativity and general relativity to do analysis is when the numbers get really, really big and the speeds get close to the speed of light. That's when we start to really witness the effects of special relativity and general relativity. And that's where you really need to use the formal equations and laws associated with this. And leave off from the old mechanics of doing the problems. Okay, so they've been experimentally verified over and over, and the old theories are really good for approximation. They've held for decades, they've held for centuries really, since the 1600s and on with Newton's law of gravity. So the older theories are good approximations. But the general rule is when the numbers get large, use SR and GR. Okay? And that's the major idea in applying relativity. So this is why, when you're doing a standard course in physics and learning engineering, you're going to work with Newton's laws, because on an everyday scale, we don't see the effects of relativity. We don't witness those, and we can use the good approximations that come out of Newton's laws. Okay, and some of the other, we don't see the speed of light making a big impact on having that constant in our everyday phenomena. Okay, so important ideas to remember. Now that we see that we need to make relativistic corrections when the numbers get really big in special and general relativity, let's start looking into special relativity and some of the development of the theory that led to the publication that Einstein did with the theory in 1905. Okay, so some of the questions that were lingering in the late 1800s had a lot to do with light. What they were finding in the late 1800s is that light propagated through space as an electromagnetic wave. It had wave properties. Okay, the particle idea got visited a little later after that in the early 1900s, started with Einstein as well. But what we know today is that light is both a wave and a particle. So the thinking in the late 1800s was, if light is traveling as a wave, it must need some sort of medium to propagate through, much like water waves need water to move, propagate through. Sound waves need either air to propagate and move through, or water to move through, etc. So the same thinking was applied to light. However, the conclusion that was made was that light does not need anything to travel through. Light can travel through space in a vacuum. It does not need anything to propagate it through that space. Okay, so they used to believe in something called the ether, and the ether permeated through space, and this is what light used to move through. So this was found to be incorrect. And we also discovered that there was no absolute frame of reference, meaning that if we did an experiment here on Earth, this would be the same sort of experiment we would expect like on the moon or on some other planet or another star, etc. And what was needed in the thinking is that there is no true measurement in any reference frame. All we could do is relate our measurements from one place to another. Okay, so before I get too far in this language, let's go ahead and think about what relativity is. So relativity is just nothing more than the procedure used to relate measurements. So if I make measurements here in this classroom, I want to be able to relate this set of measurements to another set of measurements somewhere else. So it's a procedure used to relate measurements from one frame to another. Okay, and what we mean by frame, we mean reference frame. So I should say one reference frame to another. That's what relativity is. And there's different kinds. So historically we had Galilean relativity, things didn't work out when the speeds got really fast towards the speed of light. So this failed in those tests, so good approximations, but again, when the numbers got extreme, it didn't work out. And then we get to Galilean relativity, Einstein relativity is what we have now. Which uses Lorentz transforms. And what do we mean by reference frame? Okay, so a reference frame is location in space-time where you make your measurements. So reference frame is a location in space-time where measurements are made. Okay, so you have to define your reference frame very, very precisely when you're working with physical laws. So right now I'm in the reference frame of a classroom, okay, and I might want to compare my measurements with somebody that's in a moving car or on a orbiting space station like the International Space Station. So we need to be able to relate our measurements and see that the laws of physics didn't change. So you could define your reference frame in many, many places. And some of the questions you want to think to yourself are, is there any place where things are really still? Like, is there any absolute reference frame? No, everything is moving with respect to everything else, right? So it might seem like things are stationary right here in the classroom, but I know that I am fixed to the surface of the Earth, which is rotating about its axis every 24 hours and then going around the sun every year in its revolution. And that whole system is going around the center of the galaxy, so everything is moving with respect to everything else, right? So it's really hard to think of an absolute frame of reference. In fact, it's impossible the more that we look at the cosmos and see that there is so many things moving. There is no special place for any of those objects, right? Every place is special in its own set of measurements, but we have so many different places where things are measured and measurements are taken, and we need to compare those. Okay. So one of the key foundations to building the special theory of relativity came from the Michelson-Morley experiment. This is the famous experiment done in 1887 when they believed that light traveled through the ether in space, and they tried to carry out these measurements to see how the speed of light was affected by Earth's motion. Okay, so the idea is as Earth is moving in one direction and you have the speed of light going along that same direction, you would add those two velocities and you would get something that was larger than the speed of light. Okay, whereas going around the other direction, so if the Earth is moving the opposite direction, the light was moving in a forward direction, you would subtract those and you would get a number that was smaller than the speed of light. I'm oversimplifying their very sophisticated experiment, which you can look up and read all the details. There's a lot of mirrors and laser, well, lights involved, I should say. Okay, so the idea was that you would the velocity of light measured on Earth, and here we're using the classic Galilean relativity idea on how we add velocities together to get the sum of the velocities. The velocity of light measured on Earth would be the velocity of light, whatever that speed was, which we know already, plus or minus the velocity of the Earth's speed. And then I'm doing an oversimplification here. Earth speed motion. So what would happen is you would add the light speed and the Earth speed together if they were going in the same direction, or you would have the light speed, and then you would subtract the earth speed if it were going in the opposite direction. It would be lower. So what they found was that it didn't change either way you went. It was a failure, right? So this is your relationship that they were trying to use, and this was a fail. Fail to show a difference in the speed which I'm using to represent V for velocity here. Okay, they failed to show a difference in the speed V, but they were successful in laying down this framework and saying, oh, the speed of light does not change, and there should not be anything called this ether. There's no ether out there, right? So the success was that C doesn't change. They didn't piece all that together yet. You know, they did the experimental work that helped with Einstein's theory. Okay. So another way to think about this idea, which helps you understand the concept involved in special relativity, is the old theory would be that here, let's say you're on this train car here. Call this situation 1, and I'll call this a train. Okay, a train at rest, and here you are on the train, and let's say you have a window on this train right here, and you shine your laser light. And your speed is equal to C, of course, okay? Cool, so your laser light would be your velocity of your light here. So that's the train at rest. Your second situation, and I'm going to have the train moving at V train. Let's set this train in a forward motion. Put some windows on here. Again, here we have laser light being shone out this way. That's V light. Okay, but we also have the velocity of the train. So I'm going to have a separate arrow here. I'm going to have my arrow of my V train. Maybe I'm going 500 miles per hour or more than that, etc. So the classical theory would say, okay, if you're observing this, let's say here's somebody watching this motion coming forward, they would say, oh, the speed of laser light is C. Okay, observer would conclude that the velocity of the laser light is C. Now, what about in this second situation? Okay, the train's coming towards the observer. Observer certainly slightly on the side, or they're able to move fast enough to get out of the way. So here we have the person on the train turning on the laser light. The laser light is coming along with the train's motion toward them in the direction of motion. And the observer here watching this would say, oh, the light would equal the light observed, and I should specify that as the light observed. We have to really label a lot of things, and we have a lot of subscripts in relativity. So the velocity of the light that this person is going to observe will be the actual emitted light speed, the speed of light, plus the velocity of the train. Okay? And this would be greater than the value of C, because this is C plus some extra. And what we're going to see is the ultimate speed limit is C. The speed of light. You can't go faster. And what this is wrong. This is the old Galilean transformation. And you will never be able to have that. And that's what Michelson Morley tried to do. They tried to say, oh, we're going to add the speed of the Earth with the speed of light, and we'll see that in our experiment. And they didn't. They found that no matter what, that the V light that's observed was just equal to C no matter what. It didn't matter how fast that train would go, it would still be, the speed of light was the speed of light, so it looked like it would slow down maybe as it got towards you. So some bizarre foundations here. Okay, so now after that we start getting some other people thinking about what needs to change to compensate to have the speed of light constant. So maybe we have to change space-time or some other quantities to accommodate having that constant value for the speed of light. So Lorentz and a few others came up with the Lorentz transforms. So they came up with, which is what we use in special relativity. So we have, instead of using those Galilean transformations, which I briefly just showed you in that last example, they came up with these Lorentz transforms, which allow you to take your measurements from one frame and compare them to another. So these Lorentz transformations relate laws of physics from one reference frame to another. And we could say this reference frame might be S. We could give it a label S, and we could call that our rest frame, which is purely by choice. What we do when we make measurements, we say, okay, we're going to say this is our rest frame, like perhaps right in this classroom, this is a rest frame, and everything else is moving with respect to this rest frame value. Okay, so this is our rest frame, and the other we could say is our moving frame, or other frame of reference. Okay, so maybe we're doing a set of experiments here on Earth, that's our rest frame, and we're going to compare them to the moon. Set of experiments on the moon, that would be our moving frame. So these Lorentz transformations could be a little sophisticated, but they vary by something called the Lorentz factor. Okay, so I will go ahead and write that down, because this Lorentz factor comes into play when you're doing some of the computations in special relativity, like time dilation. And they're algebraic formulas, so they're not really intense mathematically, and they give you a good idea on how to do some simple time dilation computations and length contraction computations. So we have something called the Lorentz factor here. And it has this symbol gamma. So you're going to see this in any literature that you see on special relativity. And what we have is the Lorentz factor. The way these frames translate to one another is related by 1 over 1 minus v squared over c squared. Okay, where this is the moving frame speed, and then this is your speed of light value. So this is your moving frame speed that you put in here. So this Lorentz factor is going to be used in your special relativity equations, relationships like time dilation. Okay, so the way this Lorentz factor will work with the Lorentz transforms is it will relate these two reference frames. So here's one at rest frame, like if I'm here on Earth, and here would be the moving frame, like the measurements made on the moon. So these Lorentz transforms will be, if we take a measurement in 3D space, Euclidean space, x, y, and z, in a time measurement, and we need to be able to equate those measurements to the moving frame, which are done as and denoted by x prime, y prime, z prime, and t prime. Okay, so if we define our rest frame as having these three spatial coordinates and this time coordinate, and our moving frame having these three spatial coordinates and this time coordinate, how do we relate the two? Now, it's going to have to relate in a way on how you look at the motion between the two objects, okay? How that motion of that object is with respect to that reference frame that you consider to be stationary. So are they moving in a line, or are they moving at an angle, etc.? So if we just have everything moving in the same line path as we're facing on the rest frame, we only need to transform one of these length dimensions, okay? And the way the transformations come out are, the time will be transformed in one of the dimensions and the other ones will stay the same. So using the Lorentz factor, gamma, we would get like our time transformation would be gamma times t minus v squared over c squared. Okay. And that would be velocity along which dimension, which direction, the length, width, the height, and I'll say x in this case. And then our x prime value will be our gamma times x minus vt. There's a lot of distance, rate, time, geometry involved here in this transformation. But then the other spatial coordinates just transform as is. There will be no change, okay? It would be like if there was a spaceship traveling perpendicular to me, I won't see any change if they're moving the light that way or that way. But if they're moving the light, if there's a light beam coming towards me or away from me, or a baseball coming towards me being thrown or thrown away from me, it will make a difference in that transformation. So these are how you transform your 4D space and time coordinates between the two. Okay, so we'll move on from there. We'll see how that works. Okay, published in 1905 by Einstein and based on the work of many others, the special theory of relativity is based on two important postulates. So if there's anything you could take away from the theory of special relativity, it's these two postulates. Number one, the laws of physics are invariant a fancy way of saying the same in all inertial reference frames. Okay, and what inertial means is non-accelerating reference frame. So inertial means non-accelerating frames of reference, because what happens is if there is acceleration, it would seem the laws of physics would not hold between the two, okay, that you would get different results in one compared to the other. So we want to make sure that there is no acceleration, which means the velocity is constant or zero between them. Okay, we'll find that our measurements correlate to one another. So we should find the same laws of physics in both. And number two, the speed of light in a vacuum is invariant. Again, the same in all inertial frames of reference. And the speed of light is the ultimate cosmic speed limit. Nothing goes faster than that. So these are our two postulates. And the big question is, okay, if these are our postulates of special relativity, what happens if we say this is what it is, these are the postulates, what are the consequences based on those postulates? So our next question is, what are the consequences of these statements? A lot. Okay, let's look at the consequences of these postulates in special relativity. And there's a lot. There's no absolute time or length, etc. And let's begin with the concept of simultaneity and how that is affected by the special relativity postulates. And what that means is that events that are simultaneous in one reference frame, let's say S, our rest frame, may not be simultaneous in another, let's say our moving frame. And here's an example. So let's take a look at one frame of reference, and there's many good visuals out there on this experiment. And let's say we're sitting in a train car right in the middle, and equidistant from us will be two lightning bolt strikes that happen at the same time, are simultaneous. So here's lightning bolt number 1, here's lightning bolt number 2. Here's your observer. So you're in this train car, and this train car could be moving, etc., but you're in the same frame as the lightning bolts. Okay, so this would be our S frame. Okay, next, let's make a comparison to how we view those lightning bolts if we were observing them from the outside, from an open window. So let's open up the window on the side here and change our perspective, our reference frame. Okay, so we're going to be an observer here, and here's our train car now. Obviously, my scale might be a little off. Okay. What happens in this case, if I'm viewing the train car coming towards me and I'm the observer, this is the moving frame of reference. Okay. What would I observe as far as the simultaneous lightning strikes that are occurring inside the train car? Well, you could be inside and you're seeing them both strike at the same time. Again, if you're in the center. Okay, but if the train's moving towards you, what you would observe is you would observe lightning strike happen first. Lightning strike number 1 happen first, and then you would observe lightning strike number 2 happen next. So you would make the conclusion that strikes 1 and 2 are not simultaneous. Okay, and there's many other good analogies, right? So we can be in this room, I could have 2 explosions happen. I could be in the middle of 2 explosions. But if somebody was driving by and able to see that, they'd see this explosion on this side first, if they're coming from this end, and they would see the other explosion happen after that. They would not see them as being simultaneous events. So this is really an important concept that comes out, the situation that comes out of the postulates. Okay, another consequence from the special relativity postulates, time dilation, the stretching out of time. So how does that work? Well, we use the Lorentz factor from the Lorentz transform to go ahead and compare times in 2 different reference frames. Okay, so time dilation refers to the stretching out of time when you're making a time interval measurement in your proper time frame. So here is a time interval that is called your proper time, and that's what we're going to use for our time measurements made in the S prime frame. So if you were moving away in a spaceship and you're measuring time between 2 events along your line of travel in that spaceship, that would be considered your proper time. And what we're interested in is how you compare that time measurement to someone, say, let's say that's on Earth, and we could consider them to be stationary. and we would call that the S frame. So what we're going to do is make this time comparison from proper time interval in this S prime frame, and we're going to compare that time measurement made in this other reference frame called S, or S frame. So maybe this is Earth measuring time, and this is measuring time aboard a rocket ship that's moving away from Earth, moving towards Earth, or maybe it's a time frame on another planet, etc. And this, as we saw earlier, this is our Lorentz factor, our factor that we use to transform these two measurements. And our Lorentz factor takes into consideration the speed in which this frame is moving at. Okay, and we're going to call this our frame of rest. We're going to say this is v equal to 0 in this case for our speed. Okay, so the big question to address here, do moving clocks run slower with respect to the observer? So in a loose sense, yes, there's some specific details that are, there's a more formal definition behind that. There's some details that we're glossing over here. However, it's true, and we've measured this. So there is something called the twin paradox that results from this time dilation relationship in special relativity, and that is about the measurement of time being different between two different people. And let's say we had a set of twins here on Earth, and they're both 20 years old, but one of those in the pair goes off on a rocket ship, and perhaps they're traveling at half the speed of light, and they go away, and they go away for several years. Let's say they journey for about 20 years. When they come back to Earth and have measured their time as 20 years, their proper time as being 20 years, they come back to Earth and compare their measurement of time with their twin that was left behind on Earth. They would find that that twin had a longer duration of time. Their measurement of time would be more than 20 years, and that's what we mean by the stretching out of time. So the proper time measured in our moving frame tends to be longer as v approaches the speed of light. Okay, and the sorry, excuse me. The proper time measured, this would be shorter with respect to S, okay? And the time measured in our stationary frame will be stretched out, longer, dilated. With respect to our moving frame. Okay, so in our twin paradox, we have number 1 and number 2, and okay, let's say number 1 stays home. That's in the S frame. Number 2 goes off, comes back. Okay, they would have aged significantly less compared to number 1. And that's a really good paradox to look into, and we'll do a computation that's very similar to this idea. This was experimentally verified. Luckily we had a pair of twins that NASA could do an experiment with. That's Mark and Scott Kelly. Scott Kelly has been up to space, so has Mark. Scott Kelly was in the International Space Station for almost a year, and they did studies on how much he aged compared to his twin left on Earth. And there's, a lot of variations in that experiment because other factors aged him, like the radiation in space, etc. So there are a lot of other factors that led to this not being the best sort of experiment to do. But if we had a better experiment and we could send somebody off in a rocket ship close to the speed of light and get some accurate measurements out of that, we could see and verify the twin paradox. Okay, so that's how that works. So, proper time will be shorter than this time measured in the stationary frame. This is S, this is S prime. Okay, so what are some of the experimental evidence we have for time dilation? So one of these effects of special relativity. Well, there was a long mystery that came along with this muon decay, and muons are these particles that result from the rain of cosmic rays that come through Earth's atmosphere, and cosmic rays are these particles that come from the solar winds and solar activity. So we have these charged particles that rain down on Earth from the sun, called cosmic rays, and other events in the cosmos. So we get these particles that come through the atmosphere, and then they interact with the particles in the atmosphere and produce these other particles called muons. And the lifetime on muon is extremely short-lived. So it puzzled scientists for a very long time because, you know, they'd have these muons live and then be detected on the surface of the Earth where they should not be detected. They should, their half-lives are so short that it wasn't expected to be able to detect any on the surface. But the idea was the muon was traveling so fast, close to the speed of light, so its clock ran slower than a detector or an observer on Earth. So we were able to catch, I think it's about 1 out of every 10 muon we're able to detect through the atmosphere. Okay, so their lifetime was longer with respect to our clocks, and that's from time dilation. They've done measurements aboard aircraft where they measure the time differences. So here we are on stationary Earth. We refer to Earth as our S stationary frame. Here's an aircraft with a clock, an atomic clock, flying overhead, flying faster. So that's their S prime frame. And when we compare our two clock measurements, we'll see that the time measured on Earth will be a longer duration than that measured on the aircraft. Okay, GPS satellites always have to sync their times. They're moving around and they have different speeds they're going by, so they constantly have to update their clocks by the time dilation relationship and the Lorentz factor. They have to be corrected for. Then the twin astronaut experiment, NASA finally had the opportunity to try to run this twin paradox experiment with Scott and Mark Kelly, both astronauts. Scott Kelly is the one that's been on the space station for almost a full year. So while he was up in space, they compared his time and aging and compared it to his twin left back at home, Mark, even though Mark's been to space. But anyways, there were other factors involved in the aging process of Scott, so it was not the best exact experiment done, so that was conducted. So, you know, sort of inconclusive results for that one, so hopefully there'll be more opportunity to repeat that in the future. Okay, so there's a lot of experimental evidence, but let's go ahead and do an example. Okay, let's do a little computation on how this works and look at some of the details involved in time dilation. So suppose we have a situation where we have two twins and they're able to build a spaceship that could go half the speed of light, 0.5 c. So we're going to let our velocity or speed be 0.5 c. In this case, we won't take direction into consideration yet. And then what we're going to have is we're going to have Ying, one of the twin pair, will stay behind on Earth while Yang takes the ship and goes to an exoplanet directly and back. And we're going to keep this constant speed for Yang. We're going to assume that Yang is going to keep this consistent speed and not change it in Yang's journey. And Yang measures a time span of 25 years on this journey. Okay, so how much time has elapsed on Ying's clock back at home, at rest on Earth? So here we are on Earth, okay, and we're going to have Ying out here. And Ying is going to measure an amount of time on Ying's clock back on Earth, okay? And then Yang is going out on a rocket ship, okay? And Yang is going at the speed v equals 0.5 c, okay, to some exoplanet and then coming right back. And we know that Yang measured a proper time of 25 years. Okay, so what does this clock measure? Yang's clock measures 25 years in the proper time interval. Ying's clock measures how much? So in this case, what we'll do is we'll first go ahead and remember that our time measurement in our S frame, so we're going to call this our S frame. This is our S prime frame. So again, we want to relate the measurements between these two frames of reference. So here, delta t, the amount of time that Ying measures, will be our Lorentz factor times our proper time, delta t naught, okay? So what we're going to have here is our gamma factor, and that will be 1 over the square root of 1 minus 0.5 squared over c, 0.5 c squared. I'm running out of a little room here. Let me go ahead and do this. This will equal 1 over 1 minus 0.5 c squared over c squared, a little better, times 25. And if I'm using a time of years here, I'm going to get an output of years. If I use minutes here, I'll get an output of minutes, seconds. So this Lorentz factor is unitless. So whatever units you put in here, you get out here. Whatever units you put in here, you get out there. Okay? So what we end up with is, if you do this calculation, you're going to have 1 over the square root of 1 minus 0.25 c squared over c squared, and these cancel, okay, times 25, and that should give you, if I do my calculations correctly, 1 over 0.75, because you have 1 minus 0.25, which is 0.75. You have 1 over the square root of 0.75 times 25. And what do we get as a result of that? Okay. What I'm going to do is put this value. I'm really squishing a lot of values here, so I'm going to erase this. So we have 1 over the square root of 0.75 times 25. And if we calculate that value, we will get 1.155 times 25. And we get approximately 28.9 years. Okay. Which makes sense. We would expect as much. Stationary observer with respect to one that's moving to a speed comparable to the speed of light. So of course we don't see this. This is not really something we recognize on an everyday scale, because many things that we witness are not even moving close to the speed of light. Okay, so there is that effect. So almost 4 years difference here. Okay, now what would happen? Next question is, let's say we go ahead and make Ying travel at a speed much more so. Let's speed Ying up more. Okay. All right, let's see what happens when we turn up the velocity a little bit, the speed some more. So let's go ahead and make Ying travel at, let's see what happens when we turn the speed up a little bit. And everything's in straight line motion here, okay? So if we make Yang travel at 0.9 times the speed of light. So let's say Yang is going to go at 0.9 c, the speed of light. What we want to know now is how much different the clock measurements will be. Okay, so Ying will measure a time of how many years? Well, let's see. But let's still make Yang go off and travel for 25 years. But at a much faster speed, what's going to happen? So in this case, what we're going to do is we're going to say our delta t will equal our gamma factor again times our proper time of 25 years. Okay, and our gamma factor here will be 1 over 1 minus 0.9 c all squared over c squared, and that'll be times 25. And when you do these numbers, you'll have 1 minus 0.81 c squared over c squared. C squareds cancel and you get 1 over 1 minus 0.81 times 25. And this will give you a value 1 divided by the result of the square root of 1 minus 0.081 is 1 over 0.43. And I'm just going to quote my results here from my calculator. 59 times 25. Okay. And the answer for that will give you, this will become like 2.29 times 25. Okay. And you get a value that's significantly larger. We get 57.25 years. So what we get here is approximately 57.3 years. A lot more. So we could see that more than double the amount of time measured on the clock of Ying back at home on Earth. Okay, so this gets more pronounced of a difference as we get closer and closer to the speed of light. Here we're going 0.9 times the speed of light. So if you're going to go 0.95 the speed of light, 0.96, your numbers will be dramatically more different. Okay, and then the question, okay, so how do we get to have those differences in time measurements between the two frames of reference? Well, when you think about it, it really comes down to simple geometry and how you relate your distance rate and time relationships between these two reference frames. So consider for a minute, and we have to think of the ideal situation of a light clock. And having a light clock, let's say just a simple laser light that will emit light from towards a mirror and then come back on our ship. So if we're the person in the rocket ship traveling at a significant speed of the speed of light, and we're doing this experiment, we would witness the light hit the mirror and come back down along this length called L, okay? And we would not see any difference in how the light would appear on that path. Now, however, if we look at this as an outsider in a stationary frame in frame S, and we view the moving frame S prime here, okay, and we take a look at what's happening as they're emitting the laser light, or they're using their light clock inside the ship, and we're able to see inside, we would see that light as the spaceship is moving towards us. We would see it zigzag and do this zigzag path. Because what's happening is you're emitting that light going up and down, but if you're viewing that light coming towards you or away from you, you would see the light path differ, okay? And when you do the geometry, we know this is your length L right here, but we would know that the light would move or shift in its position by amount of v, the velocity that the ship is going, which was, we did for the last problem, was half the speed of light and 0.9 the speed of light, times your delta time, your time increment, divided by 2. Okay, and then this length right here would be the actual rate of light, the speed of light, which is your rate, times your time, and that's your distance divided by 2. So you could do these relationships and use Pythagorean theorem and derive these relationships that you get for your proper time measurements and your time measured on the stationary or the S frame. Okay, so they're both using the same ideas here, except you have that Lorentz factor coming out of this due to the geometry. So some tricky thoughts to think about it. And there's a lot of really good visuals on that. Okay, so our last bits. Okay, some of the other consequences from those postulates of special relativity. Length contraction is a big one. So just like we had stretching out dilation of time, we have lengths that contract when we're comparing different frames of references. So if I were stationary here on Earth and I watched this meter stick fly by me at the speed of light, okay, depending upon my directional line of sight, it would appear to be shortened in its length. I know it's a meter stick, and at the rest frame right here, in the S frame, I can measure 1 meter. However, if we're moving to a speed comparable to the speed of light, I would end up measuring it at a value less than 1 meter. However, whoever's on that meter stick and traveling would have it still measured as 1 meter. So in the same sense, we have length contraction, and just like before, we have two values of length. So L naught or LP, L sub P is your proper length. And it's the length measured in your S prime frame, your moving frame, so to speak. That's typically a way we could sort of loosely look at it without going into some real formal definitions. Now, the other length is measured in your stationary frame. So this is the length measured in your S frame, and this is what we typically say is our stationary frame. Okay. So we have these two length values, and they're going to be a factor. The Lorentz factor is how we translate those two. Now, one of the big paradoxes that come out of this consequence is the pole in the barn paradox. And it's like if you're moving and you have a pole that's like 1 mile long and you have a barn that's 1 mile long and the doors are opened, right? And you're moving, let's say, close to the speed of light, will you be able to get that pole through the barn? Okay, so the famous one paradox that's connected with this is a pole in the barn paradox is associated with length contraction. And you can look that one up, and it's all about a barn and a pole, same length, and whether one moving frame will change the length dimension so much that it will not make it through that burn. Okay, so other consequences from the postulates of special relativity, well, there's relativistic momentum, okay, and this is also related via the gamma factor. A simple formula, relativistic energy. This is where it starts getting a little more involved. And you have your energy equations with a gamma factor involved. Conservation of energy momentum still hold, but the equations, there's a few other adjustments that need to be made with the Lorentz factor. Okay, and this last one has to do with the rest mass energy of any particle. So we know that any object that's moving has energy of motion associated with it, but a particle or some object can be still and still have an associated energy with it. Okay, and you can compute that using this E naught equals mc squared equation, where energy is equivalent to mass by this factor of c squared, the speed of light squared. And typically we see this when we're looking at radioactive decays of certain masses. We see that, you know, this mass or this atom or this isotope is not moving around, and what happens is it still has this energy and it decays off into smaller bits and particles and lets off this energy, right? So these are some of the principles behind nuclear fission and nuclear fission reactions and the atomic bomb testing. They started after they developed these theories soon after World War II. So anyways, that's just a little overview of special relativity, and hopefully that gives you a little better insight onto some of the interesting ideas associated with it.